Hello and greetings. Is this working enough? Can you hear me?
Yes.
Okay, great. Oh. Go back down here. So, I can't tell you how glad I am to see you, because it's been so many years now, it seems like forever. That was the last time we actually did a picture in person, and so that's like 2019. So some of the people you'll recognize, Ryan's there, wearing a bright red shirt so he stands out. And a lot of people aren't there, but we'll fix that.
You could hold
as
a
a breeze
picture
back.
10 years ago and I'd be in it.
Really? Okay, okay. So, the in-person edition. So I'm going to do the first half of the safety lecture, which is more kind of soft stuff, I'll say. And then we'll get into Tim, who's going to give it the hardcore rules and regulations that you better do or else. Yeah. COVID statement. Goodbye. Glad it's gone. The university policy is still that it encourages the vaccinations, the masks, and although you don't see it, but you probably noticed it in some places, they've really worked hard at boosting the ventilation up. Okay, so the first question is, I know you're here because you have to be. But why do you really need to be here? Because we're pretty successful. We don't get many accidents, not big accidents. Well, sometimes we do get big accidents. And the trouble with a lab accident, like a lot of fire situations, is that once it starts, it takes like about 5 seconds to get to that state. It's really that bad. So when you're working in the lab, you're comfortable, you're having fun, you're doing your research, but you got to realize you're still in a place that has the potential to do naughty things to you if you're not careful. The other reason to come here is Carlos says you have to be here, and you don't want to mess with him. Yes, he got me to do a picture of one of his students, and he was kibitzing and doing everything he could to mess up the picture I was trying to take, and he jumped through the frame and didn't figure that my camera was fast enough to catch him. So I use that to embarrass him at every chance I get. So, as I said, Tim's going to tell you about a lot of procedures that you really should know about. And the two of us are going to try to convince you that it's worth your time spending some time and effort on safety. As I said, we're doing so well that you kind of think, gee, nothing's going to happen. We're almost too successful. But, you know, you really got to take it easy in the lab because things can go bad quickly. Now, before this year, I talked to well, I'll call the frontline staff, the staff members who either work in labs or deal with labs. And I said to them, tell me one point, one tip that you'd like me to pass on to the CHEMENG researchers. Not just one. So what I got, EOHSS, this was Leah Allen, who was our contact person in EOHSS. She's a chemist. She worked as a chemist and mass spectroscopist for many, many years. What she said was protect your eyes. That's usually what I say to you guys, but she's noticed in the last year there's been an uptick in the number of splashes, fumes, vapors, which is kind of a sneaky way to get in. You're dealing with something, exothermic reaction, and it raises up a vapor, and also debris in the eyes. And she doesn't know why, but for some reason it's gone up in this last year. So what she said is her one tip to you is protect your eyes. When I asked Justin, our new machinist, and Paul Gatt, our machinist who's easing into retirement, they all said avoid complacency. They see people do something, do it over and over and over again, everything's fine, so they get a little sloppy, they get a little complacent, think nothing will go wrong, and something goes wrong. So when you're doing something repetitively and you're successful, it's really hard to keep yourself motivated. So that's what they told me to send on to you. Mike, in the instrument shop, computers and whatnot, what he said is, don't stick your hands in it and grab a hold of something right away, because he sees people where he's got equipment cracked open, and there's power to it, and people put their hand in. Or maybe there isn't power to it, but there's a capacitor in there, which is stored power. So until you discharge it, it's still dangerous. So what he says is the first thing you do is look. Then, gingerly, you can start putting your hands in and do things. Tim worries about distractions in the lab. So he worries about people arguing with each other, messy workplaces, anything that kind of takes your attention away from what you're doing. So that's his one takeaway. Yeah, this is a new one for me, because in the last year, I've come across a couple of what I think are unusual situations where somebody, kind of a junior researcher in a lab, had something go a little bit wrong and got some advice from a senior researcher, and it wasn't such good advice. Like what we call suboptimal advice, I should say. So I think you got to realize that you're the one bearing the consequences for what you do. So if somebody tells you to do something and it doesn't sound quite right, there's a pretty good chance that it isn't right. And you should check it out. So don't always just blindly do what somebody tells you. If it sounds good and it's somebody who you think is really smart about these things, okay. But unless you're sure, I think you ought to check it out. And this is completely new. I've never even thought about that before, but it seems to have happened this last little while. So there's my safety chart wrapped up. Don't hurt yourself. There's millions of pages, federal, provincial, about what you should do for safety. And it's just overwhelming. And you look at it and it puts you off. It's too much. But it really boils down to, don't hurt yourself. Tim and I know most of you, or we will know many of you. We like you, and we don't want you getting hurt in the lab. You're going to have a lot of fun doing your research, but just do a few things that will protect you. So don't hurt yourself. If you are looking after yourself, you probably, as a side effect, will not hurt anyone else. You won't do something that then splashes over on somebody else. So you don't even have to think about being nice to other people. Just don't hurt yourself, and you probably won't hurt anybody else. Protect your eyes. That used to be my one piece of advice, somebody going in the lab, just protect your eyes. They're so sensitive. Something, a little acid on your hand, big deal. A little acid in your eyes really is a big deal. If something happens that kind of shakes you, that you haven't seen before and you're not sure about, get help. And it doesn't have to be highly trained help in your area. Get somebody there. If you've got a spill, something's happened in the lab, a fire, something like that, having people around is very, very comforting. So just get somebody. It'd be nice if you got Tim or I, or if you got your supervisor or a senior, say, postdoc in the lab. But if you can't get them, security guys know the drill. Anybody there, cleaning staff, electricians, anybody, just having somebody there with you when you're not alone makes a big difference. And unfortunately, after everything gets taken care of, there's going to be paperwork. There's safety incident reports and whatnot. And Tim and I tend to want people to process paperwork, incident reports, even for close misses, near misses. So even if something didn't actually happen that hurt you, but could have, we like that to go in, because we discuss these incidents in the Joint Health and Safety Committee meeting for the faculty. And these near misses are a great learning opportunity because we find out what not to do, and it didn't cost anything. Nobody got hurt, nothing got damaged. So if you have something like that, put in the incident report. I know it's a pain in the neck to do, but it really helps everybody else, especially if it's something unusual, which people wouldn't think was going to be particularly dangerous, but it went bad on you. Now, I was thinking about what has helped the most to boost safety up from Second World War level. Chemists were under much more hazard in the lab than they are now. Starting about the late 60s, maybe mid 70s, things got much safer in the lab. And I think what happened was fume hoods, engineering control. So used to be, you worked in a lab and there were fumes, you put up with it. And if you said, gee, that's kind of smelly, you were worried somebody would say, what a sissy, suck it in. You don't do that because you're sensible. But that's what people used to do. Fume hoods, and we got a lot of them all over the place, and the fume hoods pretty well dictate how much work you can do in a lab, research work. Next one is attitude. People don't eat in the lab anymore. They don't say, as I said, you're a sissy if you don't want to breathe toxic fumes. You have a much greater sensible attitude than people did, say, a generation ago, 30 years, well, maybe a little more than 30 years ago. So attitudes have changed a lot. And eye protection. It started out, you walked around the lab like this. Then you wore glasses. Then you wore glasses with removable side shields. Then you wore glasses with non-removable side shields. Then you worked your way up to goggles. So there's been this progression as people have realized how if you're in a lab and you got safety glasses on, they protect you this way, but somebody beside you does something goofy and it comes in through the side. So, to be proactive, to not wait for something to go wrong, but to do things that will stop it from going wrong, guard your eyes. Talk to your boss, figure out what is the appropriate eye protection in your lab. It's different for the machinist than it is for people working in a research lab. You're the guys who are the experts really about this because you're in the lab every day. So if I'm going to ask somebody what to do, I'm not going to ask the guy who's sitting in Gilmore Hall with a suit, who isn't in the lab. I'm going to ask the guys like you who are actually in the lab, say, what do you do? Because you actually have your hands on. So don't wait for somebody else to tell you what to do. Be proactive about this. Decide what can you do to make things safer for you and everybody else. You bear the consequences of it. If something goes wrong in the lab, you're there. The people in Gilmore Hall aren't there. So as I said before, if something does go wrong, get some help. Water fixes almost everything. Water's available in large quantities, bit of pressure behind it, you can really slosh things off. It doesn't matter if the stuff isn't all that soluble in water, there's so much water available, you can really push it off. There was a trend about 30 years ago to get cute and say, gee, water's not such a good solvent for this, so we're going to have bottles of ethanol and you use that and that will dissolve the stuff off, and that turned out to be a disaster. Because in many cases, instead of flushing the chemical off, it spread it around and the chemical got absorbed through the intact skin. And the amount of absorption depends on the surface area, not the quantity. Unfortunately, there's always paperwork. And Tim can help you with the paperwork.
Sure.
Yeah, you notice I said Tim can help you with the paperwork. Not me can help you with the paperwork, but either of us can help you. And the other thing is that we've learned from the COVID years, if you get sick, if you don't feel well, let your supervisor know, let people know that you're going home. Go home, look after yourself. I'm not talking about having COVID, I'm just talking if you don't feel well, lab is not a place to be. So why is it that people resist safety? I think a lot of the reason is that nobody likes being told what to do, right? You're smart people. You're capable people. You don't want somebody like me or Tim telling you what to do. We're so successful now, the likelihood of something happening, an accident, you observing directly is really low. The likelihood of you knowing somebody who had an accident is low. The likelihood of you knowing somebody who knew somebody who had an accident is low. When you get really low probability, people kind of jump to the conclusion there's a 0 chance of an accident happening. So it's really hard to maintain your motivation when you're good at what you're doing in the lab, when there aren't accidents, when you don't even hear of an accident. So you have to watch that kind of prejudice. I think some safety professionals still will try to tell you that safety procedures are not in the least inconvenient, they're just wonderful. Well, that's not true. Putting masks on takes a little bit of effort. The machinists, at the end of the day, the safety boots they wear leave their feet sore. Hard hats on the construction site leaves a line around here. Safety goggles leaves a line. Yeah, there's inconvenience. It's a price you pay to buy yourself protection. And that's the only rational way you can look at it. The other thing is complacency comes in many different ways. One, it can be that you've worked on something over and over and over again, so you've never had a problem. Maybe you've never had a problem even if you're doing things not quite right because you got lucky. Or maybe you did have a good procedure, but over the years you kind of slacked off a little bit. Or maybe you're one of those people who's not all that sensitive to some chemicals that other people are. There's a huge distribution of sensitivity to things like carbon tetrachloride. Some people can almost bathe in it. Used to be fire extinguishers were full of carbon tetrachloride because it's a chlorinated hydrocarbon, has no flash point. It's hard to believe that we were spraying that around to fight a fire at one point. That's how safe people used to think it was. But then some people turn out to be really hypersensitive to it. So I've said most of those things. The last one is that the risk is the probability times severity. So low probability event, which is really severe, like that fire in the lab I showed you, even if the probability is low, you really want to avoid that because the consequences are just so huge. On the other hand, you have some things where the probability is kind of higher. Maybe you're working with something and you might nick your finger occasionally. So the severity isn't that high. So you look at it and say, do I need to guard against that? If I put a guard in, is it going to make it clumsy? Is it going to make it more likely for me to have an accident? So you have to do these calculations yourself. So what are the top ways to get hurt? Mainly breathing in stuff. Even though we have fume hoods, you might have something close to the front of the fume hood. You might be boiling something, enough kinetic energy that it comes out, and you snort it up. So that's what you have to worry about. We have some labs now that are working with big equipment, heavy equipment, like 109, Thompson's group, extruders and things like that, the machinists. You could drop something on yourself. You could hurt yourself that way still. I don't think anybody swallows poisons anymore. They don't eat in the lab. Bread, by the way, in a sandwich is a really good absorbent for fumes and things like that. So people don't eat in the lab. They don't drink out of a beaker thinking it's cute to toast each other and stuff like that, forgetting that somebody had benzene in the beaker before them. You know? You don't often get corrosives on your hands to the point that they cause direct damage. You have to worry about things that are sensitizers, like isocyanates and whatnot. You work with them, everything's fine, then one day suddenly you develop an allergic reaction to it. And that means after that point, you know, one molecule is going to set you off, so you almost can't work with it anymore. So the sensitizers, you really got to be careful with because they don't appear to be that bad. But once they trigger a reaction in you, that's it. And I don't think anybody smokes in a lab with an open bottle of ether on the other side anymore and blows himself up that way. And that's been a long, long way in the past. And by the way, the smoking in the lab isn't bad because it's going to light up the ether trail. It's bad because you got the cigarette in your face and the smoke is getting in your eye, so you put the cigarette down on the bench top, continue working, and you pick it up, not realizing you put it into some spilled, say, potassium isocyanate solution, and then take a puff and whoop. So, you might be doing something where you looked at an old paper that gave you a recipe, and back in the days when this paper was written, they were using benzene as a solvent. So, benzene is not good. It's a carcinogen. It's really not good. But maybe you can use a different solvent. Maybe you can use chloroform, no flash point. Maybe you can use toluene, reduces the toxicity way, way down. So, first thing to do is, if you've got something which is a little bit iffy, see if you can change it, if you can do something else. Make sure you use your engineering controls. Those are the ones that you don't have to do anything for. They're there and they work. So that's mainly for you, it's fume hoods. The personal protective devices are eye protection and gloves, maybe double gloving. If you're working with something, say a neurotoxin, and you strip off the outer glove every once in a while, give a sniff, see if there are any pinhole leaks there. So in some cases, that's the only way you can protect yourself. In other cases, if you're working with a fume hood and you've got safety glasses or goggles on, you've got 2 layers of protection. The engineering control keeps it away from you. If something fails there, the safety goggles will keep it from getting right in your eyes. And the best thing that you have is that you're smart. So you can think your way through things. Now, if you go out in industry, say go down to Sarnia, you got people there with like a grade 8 education. But they're trained really well. They're drilled really well. If the chlorine gas alarm goes off, they look up at the windsock and they go upwind. They don't talk about it. They don't discuss it. They've just been trained, you know. Hear that alarm, go that way. Thing. You use a huge variety of chemicals. So you can't be trained like that. You can't train people who don't understand the chemicals for every different chemical. But you're smart and you can think your way out of the problem. Thinking your way out after something goes wrong frequently doesn't work because in an emergency, people tend to panic. They freeze up. They don't make the right decisions. This happens all the time. The time to think about it is ahead of time. What if this happens? What should I do? That's a very comforting procedure because when you go and you're in the lab, you know what to do. You're confident. Okay, I got it worked out. I know if this happens, I'm going to do this. If somebody drops a bottle of acid here, we're just going to get out. We're not going to try to clean it up right away. If it's 500 mils of conch HCl, we're getting out, closing the lab, calling people, and then deciding what to do. So have the procedures in your head, and they will, as I said, stop you from panicking or making the wrong decision. So WHMIS was an amalgamation of several acts at the federal level and the provincial level. And the purpose of it, even though when you and I see it, it looks like this labyrinth of words and stuff, but it's actually pretty good, the idea behind it. You got a right to know what's going on, right? Don't say, employers can't say, well, don't worry about that, but just go and move that tank of liquid that's foaming and all the birds around it are dying. You'll be okay. Just go and do that. No, you got a right to know what you're doing. It identifies what are your responsibilities. Remember, there's the employer, McMaster, supervisor, your faculty supervisor, the worker, you, and coworkers too. If you see somebody in the lab doing something goofy, I think you have a moral duty to tell them about it, but actually, it's actually now enshrined in the law. You have a duty to look after them. So now all the responsibilities are listed, and you have a right to refuse work. It doesn't mean that you can say, gee, I don't like that, or I want to go away for the weekend. It means if you're really, really concerned about it, and you bring it to your supervisor's attention, and they explain it to you that it's okay, but you don't feel right about it, and you just can't reach some agreement, then yes, you can refuse work. And then a Ministry of Labor inspector comes in, and sometimes they agree with you, sometimes they don't. I've never heard of that happening in any of our labs. It would be very unusual because people collaborate a lot, they talk back and forth and finally reach some agreement about how things should be done. We used to have these really nice, simple ratings like the Hazardous Material Information System. It was kind of like the fire triangle. And the rating would go 0 to 4. So 0 to 1 was pretty innocuous. A 2 was your regular run-of-the-mill solvent. A 3, now you watch out for it. A 4, I wouldn't like summer students working with it if it was a 4. And if you're a graduate student, postdoc, you gotta be careful. The new globally harmonized system, which the whole world has now, was introduced to simplify things so that there weren't going to be confusions and whatnot. But the first thing that it kind of did odd was a 1 on the globally harmonized system is really bad. And a 4 is not so bad. It works on the quantity of material required to hurt you. So 1 means a little bit of material will hurt you. 4 means you got to ingest a lot. And it's roughly a logarithmic scale. Not exactly, but roughly. Okay? So when it was first introduced, there was a lot of confusion where people were looking at SDS sheets, and they were used to the old MSDS sheets, and a 1 on the MSDS sheet meant not a big deal. And they were seeing a 1 on the SDS sheet, and they were saying, not a big deal, when it really was a big deal. I don't see that anymore. All the safety reports we have, I don't think anybody's made that mistake any longer. So, out of mercy for you and Tim and I, we changed the way the safety reports are done. It used to be you had to do them from scratch, and I was looking at them one day and I realized that a lot of the stuff in there is the same. Everybody's report has the same stuff that we expect you to put in, so Tim came up with the template. And all these things that are the same, why make you write them out again? So now we're pretty well asking you to just tell us what you're doing. So, a couple of paragraphs so we can understand if it's reasonable or not. And then if you got chemicals in there, list down there which ones are toxic, any unusual properties, are they skin absorbents like DMSO, that type of thing. So it's a lot simpler for you, and it's a lot simpler for us. The job hazard analysis, there used to be some confusion that that was only for people who were staff, or if you were TAing a lab. But now the university says everybody has to do this JHA, job hazard analysis. You go online, you click off what the potential hazards are, and it generates, like typically a one-page list, and you sign it, and your boss signs it, and it goes over to EOHSS. So it's an extra thing for you to do, I know, but it's not a big extra thing. Lab safety info sheet, it's on the door. That's really for the first responders. So if something goes wrong and the fire department comes in, they'd like to have a rough idea of what they're walking into. It's also good for people like custodians and whatnot who really, they need to know if this is a biosafety lab or not a biosafety lab, or if you've got some really noxious chemicals in there. So it's the right to know idea. Tim is going to talk to you about labeling. Oops. In Ontario, there's 11 designated substances, and that means things that are considered so nasty that there's no safe quantity no matter how small. You can work with them, but you got to do a report on it. The report is filed in your lab or with your group, and if anything goes wrong, then the Ministry of Labor Inspector, when they come in to do an investigation, asks to see that you did the designated substance assessment. Around here, the ones that we're most likely to see, well, not so much anymore, but benzene would be one. Isocyanates, a lot of people, isocyanates is a precursor to polyurethanes. Silica, which is not like beach sand, it means small silica, crystalline and respirable. So small particles that you can get into your lungs, and they have to be crystalline because they're the ones that are going to cause the damage. The smiley face means Tim takes over.
Can I get the microphone?
You certainly can.
Thank you. Okay, good morning. Thank you for being at the presentation this morning. And I'm going to talk to you about a few other matters involved with safety. My part of the talk is more specific directions on how to do things. So I'm going to start with disposals of sharps and needles. So there's two general types of sharps we have. One is metal sharps, and most of those are needles, and the other is broken glass. If you're disposing of either of these two things, the number one rule is you cannot put them in a waste container like the garbage cans over there. And the reason is it's a hazard to cleaning staff. If they're picking up those bags, they're going to possibly stab their hand with it, and that's very, very bad, especially if there's chemical or bio on those surfaces. Okay? So you must place them in proper sharps containers, Generally, in most labs, we have two types of sharps containers, one for glass, one for metal, and you have to sort them out into those. You can get these from science stores, so over an ABB. I think you can also order them from VWR or Fisher. You have to label them as bio or chemical, so you have to specify the content. If it's strictly chemical, you can put one of these labels, one of these orange labels on these. So if there's no biohazard in your sharps, you can put this on the outside of the container. If there's anything with any biohazard, then they have to be disposed of as biohazard. And many of those containers actually have biohazard symbols on them already. Okay? Full containers would be labeled and taken away from your lab by the waste management company that we use. Okay? So hazardous waste management and disposal. If you have leftover chemicals, either ones that you're done with and not using, or ones that have been through a process, some reaction or something that you've collected after a reaction, we don't, as a rule, recycle them or reclaim them or simply designate them as non-hazardous. Okay? They have to be put away and properly sequestered. We don't put them in sinks, drains, toilets, or garbage pails. The main danger here is, one, is risk to people who might be handling those, but also the big risk is environmental hazards. So we don't want to pour things like lead or whatever down the drains, because this gets into the water supply and it's toxic to the environment. If you're not sure, you can speak to myself or Doug, and you can also speak to EOHSS for more information on what needs to be handled properly for disposal. Okay? So waste management, you're going to put these yellow labels on any of the waste bottles that you have. The labels have a little red number, and that's what you're going to use as an identifier on the form that you fill out for inventory. You shouldn't store waste for the lab for long. One of the things I see quite often is, when I do safety inspections of labs, is I'll see containers that have been sitting there for months and months or years with yellow labels on them, and they're full. There's no reason that you should be keeping those in the lab. They can be taken out every Tuesday, so you should make sure that those are regularly getting taken. You need, if you're dealing with organic chemicals, you need to segregate halogenated and non-halogenated solvents. And that's because the halogenated ones are actually quite a bit more costly and have different procedures for disposal once they're picked up by the disposal company. So we don't mix those two classes together. Never add waste to a bottle with unknown contents. You don't want unknown reactions happening. You always want to be dealing with things where you know what is in the bottle and what you're putting in there. Never add waste to a bottle, or sorry, I already said that. Wear safety goggles, gloves, etc. when you're handling waste. And if you're transferring a waste bottle from one lab to another, use a safety carrier. Don't just carry it down the hall. Waste management and disposal. Chemical waste is picked up from labs every Tuesday, typically between about 9 to 12 in the morning. You need to fill out an inventory form that references the number that's on these tags. And you need to email a copy of it to EOHSS before 9 a.m. on Friday if you want something to be picked up the next Tuesday. They will not accept unlabeled waste. You have to have the yellow labels on it. Even if it has a commercial label on it already, you always have to have proper yellow labels, and you have to identify the contents as accurately as you can. And you or somebody from your lab group needs to be present when the waste management company comes to pick it up. In many cases, they actually will simply refuse to pick things up if they don't have the person there who's responsible for who sent in the forms, because they may have questions about what's in there, so they need to know this. Okay? Disposal of empty glass bottles. When possible, try to recycle them. So a good use of them is to use them for chemical waste bottles. So these would be the bottles that we use for solvents and the Winchester bottles and things like that. You need to rinse them with water or a miscible solvent and deface the labels. So defacing means scratching off the label or marking it out or covering it over. If the contents were toxic, all of the rinse has to be disposed of as hazardous waste. So you need to take the rinse water, put it in a container, and that has to go out as hazardous waste as well. Empty solvent bottles, once you've rinsed them, can be placed in the fume hood with the lids off, and you can allow them to simply evaporate. So that's only for traces of solvent, not for liters or large amounts of it, but just for traces or residues. And if you want to actually just dispose of the bottles, you need to put one of these green labels on them. You can get these from ABB stores, science stores, okay? And you're going to put them in the corridors on Thursday afternoon, and the custodians will pick them up on Friday morning. But in general, I think a lot of us in the labs reuse the bottles because it just kind of makes sense for hazardous waste bottles, okay? The inventory tag system. All the chemicals in commercial bottles or commercial containers have what's called a HECMET or HECMET label on them that the university places on them. They're little barcode tags, and some of you might not even notice them because they're fairly small. You need to remove those tags before you dispose of one of these containers. And you also need to go in and remove the chemicals from the inventory. There's more details at the link here, but you can either put the tags on fix the tags to a sheet and send it to EOHSS and they can remove them, or you can log into the HECMET yourself. If you don't have an account, you contact EOHSS and they will provide one for you, and then you can remove things from the inventory. All chemicals coming into the university are labeled by shipping and receiving before they get to you. So look for little barcodes on your chemicals. And if you're not sure about any of this, if what I'm saying is maybe not clear because you haven't seen these, Doug and I can help you. Ask us to come down to your lab and I can show you where the tags are or how to put labels on things or what kind of bottles you should be using for waste. It's one of our jobs to do that. Biomedical waste transport for the solid waste. So that would be things like, I don't know, pipettes or items that are contaminated with solid items that contain bacterial cells or living cells, level 2 BSL. You're going to collect and label the waste in appropriate bags. I believe these are the bright yellow ones that are provided. And you're going to take it down to JHE 137. That's our bio-waste transfer room. Bio-waste should never be allowed to sit for more than 3 days in your lab. And solid bio-waste is removed every Thursday before 8:30 a.m. So you have to have your waste in there by Thursday, okay? So that would include any kind of solid materials with cells, but also things like sharps. If you have needles and things like that inside a sharps container that have bio, you also need to dispose of them that way. Okay? Liquid biomedical waste is slightly different. So this would be things like solutions that have living cells that are BSL2. You need to neutralize the waste by adding bleach to it. So this is like the same bleach that you use for laundry bleach. You mix it 10:1 with the solution and make sure it's thoroughly mixed. You let it sit for a 20-minute contact time, and this inactivates any viruses, bacteria, or cell that are in it. And then you don't pour this down the drain. An older procedure is we used to pour it down the drain. We've been told that that's no longer allowed according to local bylaws. So you have to place it in a chemical waste container, label it with one of these, and it will be picked up by RPR Environmental on Tuesday mornings, as with your other chemical waste. Okay?
Tim?
Yeah.
There's a procedure now, if you don't want to deactivate it, they can put it in the yellow pails.
Oh, right, I forgot about that, yeah. So,
and then it would go through
okay.
the bio-waste disposal
okay.
with no further action by you. The only trick is the lids on these big yellow pails are one way. So if you fill it halfway up and put the lid down, you can't get it off later to get the rest of it. So fill it up, not right to the top, about 90% full. Then you put the lid on, that locks it in, and then it can go in the BSL stream.
Okay. Okay, so what to do in the events of accidents. If it's a small accident, make sure you tell someone, ideally your supervisor, but also the people around you, so that you can get help. A big accident, so something with an injury, a fire, a spill, you're going to either dial 88 by landline or use the main number, 905-522-4135. There's also an app for Android and Apple that you can have on your cell phones that has that number preset in it. So you can contact for help from the university. If there's a fire alarm, you need to leave the building, and you need to make sure everybody in your lab or working group are leaving the building, and you need to stay back from the building and away from the doors. If you have COVID symptoms or you've identified as you've had a positive test for COVID, you need to tell your supervisor. Injuries and accidents. Minor injury, first aid. I'm a first aider. Paul Gatt is a first aider. And Tammy Ferrer in ABB 203 is a first aider. We're all qualified and up to date with the first aid. You need to inform your supervisor. You need to investigate the accident with your supervisor, because even a minor injury, like a cut on your finger, is something that you have to report. And you have to fill out the incident and injury report. Critical injury. So critical injury is a severe injury. There's actually a specific list of what constitutes it. But I think, as Doug was saying one time when we previously talked about it, it's something that really shakes you up. It could be things like if somebody gets hit in the head and they're dizzy or they're unconscious, if somebody loses a large quantity of blood. I don't want to get into details about this because I don't like talking about medical things, but it's a severe injury. You need to get medical attention immediately. Skip the first aid part, call the emergency numbers, and they'll get EFERT and ambulances here to help you. You need to secure the accident site. You need to inform your supervisor as soon as possible. And a follow-up would come from a worker-certified member of the Joint Health and Safety Committee, your supervisor, and the Ministry of Labor that would submit a final report. Doug?
Nobody knows what a critical injury is, the definition. They're kind of weird, broken arms,
Yeah.
whatnot. So that's why it's really good to call security. They know what a critical injury is. So they will tell you whether they have to secure the site or not. Because you're not really thinking about that if something's gone wrong. So once again, get help, get these special constables over, and they will instantly know what has to be done in that. You shouldn't have to worry about that.
Yeah. Okay. Fire safety, if you hear an alarm, get out and stay out. If you find a fire alarm, activate the pull station. Leave the building by the quickest and safest exit, and make sure other people that you're working with do the same. Don't use the elevators. Stay well away from the building. Again, call 88 or 905-522-4135 and report the location of the fire or the incident, and don't re-enter the building. Even if the alarm stops going off, do not re-enter the building until security gives an all clear. Okay, so where do you get info on all of these safety things that we've talked about in this presentation? From your supervisor, from your lab mates, from department staff, from SDS sheets, from EOHSS, so that's the health and safety department here on campus, from general technical sources. And there's some links down at the bottom of the page here that you can also follow up that will give you information about things that are going on campus and specific information about safety. What's the minimum that you need as a new researcher? You need your WMIS training, fire safety training, chemical handling and spills, ergonomics. I don't know if I need to read this whole list, but all of this is online, and all of this can be, basically you log in and you watch this online, but you need to have all these things. And some of these also have an expiry on them. So if you haven't taken them for more than a certain number of years, you need to retake them, okay? And at the bottom here, figure out what's going on, and also your safety report. So your safety reports, we have copies of it on the CHEMENG website. You're going to have your supervisor review it, submit it to me and Doug. We will review it, and then send it back to you before you start your work.
Well, with the signature of the work.
With the signature, yeah.
And the signature of the faculty supervisor, you can start work right away. Because that's down the line of responsibility for equipment.
Mhm.
We may get back to you. We may have questions right away. We may not have questions right away, but there's so many of them come in that Tim and I can't keep up with them.
Yeah.
So rather than making you wait for days or a couple of weeks, on the strength of your signature and your supervisor's signature, you can get word right away. But we probably will have a couple of little questions.
Some specific safety training, depending on your work. Biosafety level 2, if you're dealing with biosafety. Gas cylinder handling, that's actually a common one because most of the labs use gas cylinders. Hydrofluoric acid handling, not so common, but if you are working with it, you absolutely have to have that. And everybody in your lab, even if they're not working with it, has to have that. Laser safety,
And you have to let EOHSS
Yeah.
know, and they will put a kit in your lab,
yes.
an HF, a big red kit. That's not so much for you, it's for the first responders. So when they come into the lab to deal with an HF injury, they'll have a kit. They know exactly what's in there and they're familiar with it.
Yeah, it's mostly calcium gluconate and things like that that can neutralize it.
And the calcium gluconate goes bad after a while.
Mhm.
It doesn't have a very long shelf life.
Okay. Machine guarding awareness, job hazard analysis, and you can register for any of these on workingatmcmaster/EOHSS. Okay. Safety report. I know we're getting close to the end of the class, and some of you are getting a bit restless, but please just bear with me for a couple of minutes. Describes what you're doing, gives a chance for you to think through your procedures before you do them. They're reviewed by the Departmental Safety Committee. Typically, that's me and Doug. And the links and the forms and instructions are on the link below on our CHEMENG website. Okay. JHSC, or Joint Occupational Health and Safety Committee. So Doug and I are members. I think Justin Bernard is also a member as well, and we have faculty members in our department. It's a committee that conducts regular inspections to identify hazards. So if you see me coming around with my little tablet and I'm going into your lab and you wonder, why am I here and what am I doing? It's because I'm looking for signs of safety problems in labs or offices.
And the province makes us do this.
And the province makes us do this, yes. We have to. All employers need to do this. Obtain information from the employer about workplace hazards, make recommendations to the employer, investigate work refusals and serious accidents, obtain information from workers, WSIB, and review the safety training programs annually. Okay? Our departmental health and safety committee consists of Doug, myself, Dr. Ghosh, and Justin Bernard.
And we're always looking for extra members.
Yes, we are.
And we were approached by the union who looks after postdoctoral fellows that there was some interest in serving on there, and I didn't hear back from anybody. But if you're a member